Hello, everyone. This video is for my Rowan University students. This is the second video on chapter number 10 on hypothesis tests. And what we're going to do today is we're going to review how to do a hypothesis test when we have a research problem involving a population proportion. Okay, so this is our task for today. I will show you the 6 steps that we go through to come up with a hypothesis test and a conclusion. And then we'll do some sample problems. All right, so what we're going to do now is I'll share the screen with you. All right, and let's go right to the our PowerPoint for chapter 10. So I will post this PowerPoint next week, so you can actually review it. But for now, I'm on slide number 23, and this is called Large Sample Hypothesis Test for a Population Proportion. Okay, so let's go ahead and make this into a slideshow. All right, so what is the fundamental idea of hypothesis testing? Well, once again, we create 2 hypotheses. It's called the null hypothesis, which is typically the status quo hypothesis. Then we create an alternative hypothesis, which is in most cases the research hypothesis. This is what the researcher is trying to see if it's true or not. And there has to be enough evidence to reject the null hypothesis and to support the alternative hypothesis. Now, if you remember from last time, if we do reject the null hypothesis and we find enough evidence to support the alternative hypothesis, we could have made an error. In other words, we have rejected the null hypothesis when the null hypothesis is actually true. That is called a type 1 error. And we also talked about the probability of this type 1 error, which is called alpha. Another name for this probability of a type 1 error is called level of significance. So these are the types of terms that you need to know. It's defined in the textbook. But when we go through the problems, of course, I'll use these terms. Okay. Now, if we don't have enough evidence to reject the null hypothesis, it means that the sample data that we observed could have occurred quite naturally through variation, with the null hypothesis being true. However, if it seems highly unlikely that our sample data came from the null hypothesis being true. In other words, if we reject the null hypothesis and it's very unlikely, let me say it again. If we reject the null hypothesis because the probability of the sample data is so small, it seems unlikely that that sample data occurred with the null hypothesis being true, then we go ahead and reject the null hypothesis. That's the whole idea of it, is that it seems so highly unlikely that the sample data that we get has occurred with the null hypothesis being true that we reject it. Okay, so that's the 2 decisions. Either we reject the null hypothesis or we do not reject it. And also remember that if we do not reject the null hypothesis, it doesn't mean we accept it. Just like in a criminal trial, if we do not find the person guilty of a crime, it doesn't mean they didn't commit the crime. It's still possible they committed the crime, but the police and the prosecutor and so forth did not find enough evidence to convict the person. All right, so either there's enough evidence to reject the null hypothesis, or there isn't enough evidence to reject the null hypothesis. And those are the only 2 decisions. Now, if we're going to be looking at a population proportion, if that's what the problem is all about, we have to use the sampling distribution of all possible samples, and we list all of their sample proportions, and we come up with the sampling distribution of p hat. As you probably remember from a past video, the mean of the sampling distribution of p hats is equal to the population proportion. The standard deviation of the sampling distribution of p hat, which we call the standard error for p hat, is the square root of p times 1 minus p divided by n, right? So p is, now in this case here, as opposed to when we used our confidence intervals, what's going to be inside the square root here is not p hat, but p, the hypothesized population proportion. So what we use inside this square root here for hypothesis tests, we use the actual hypothesized population proportion, right? And of course is our sample size. And of course, one of the requirements is that our sample size is less than 10% of the population. But another requirement is that n times p and n times 1 minus p must be greater than 10. That's something we discussed last time. All right. And if we have determined that n, and then that's what they mean by n is large. N times p and n times 1 minus p must be greater than 10. And then we can say the sampling distribution of p hat is approximately normal. And then we can use, to answer questions, we can use the normal CDF to come up with probabilities. Okay, and that's what we're going to be doing. All right. Now, the standardized Z that we're going to use in hypothesis tests has the following equation. The numerator is going to be our sample proportion that we got from our sample that we selected, minus p, which is going to be the hypothesized proportion. All right, it's that number that shows up in the hypothesis test, both for the null hypothesis and for the alternative hypothesis. And the denominator is our standard error. It's the square root of our hypothesized proportion times 1 minus the hypothesized proportion divided by the sample size. Okay. So let's just do an example here. It says, in June 2006, an Associated Press survey was conducted to investigate how people use the nutritional information provided on food packages. Interviews were conducted with 1,003 randomly selected adult Americans. So our sample size N is equal to 1,003. And each participant was asked a series of questions, including the following two. Question 1, when purchasing packaged food, how often do you check the nutritional labeling on the package? And question 2 is, how often do you purchase food that is bad for you even after you've checked the nutritional labels? Okay. All right, anyway, it was reported that 582 people responded frequently to the question about checking labels. That's question number 1. And 441 responded very often or somewhat often to the question, that's question number 2, about purchasing bad foods even after checking the labels. All right. Based on this data, is it reasonable to conclude that a majority of adult Americans frequently check nutritional labels when purchasing packaged foods? So the question here is about question number 1. So that means that the 582 out of the 1,003 are the ones who responded to question number 1 frequently. They frequently check nutritional labels when purchasing packaged foods. All right. Anyway, because the question is asking, is it reasonable to conclude that a majority, now majority means what? Greater than 50%, right? I think you can all agree with that. So that's going to be on our alternative hypothesis. You see that p is equal to 0.5 for our null hypothesis. There's always an equal sign there. And our alternative hypothesis is that p is greater than 0.5. All right. P is the true proportion of adult Americans who frequently check nutritional labels. Right? Why do we use 0.5? Because it mentions our p is greater than 0.5 because of the word majority. You see the word majority, and it's a proportion question. It's always going to be 0.5. Greater than 0.5 is the majority. Now, going back to the previous page, 582 people responded frequently to that question. And so p hat is going to be 582 divided by 1,003. So that's our sample proportion. Okay. Now, we're going to test to see if this sample result seems to be basically normal variation around a population proportion of 0.5. Does it seem reasonable that 0.58 would be reasonable result from normal variation of samples around the population value of 0.5? Or is it so much higher than 0.5 that we have to reject the idea of p is equal to 0.5? In other words, we reject the null hypothesis and we conclude that our population proportion is actually greater than 0.5, right? So that's what we're going to be doing. We're going to see if this, and the way we're going to do it is we're going to take the probability that p hat is going to be bigger than, at least as big as 0.58. We're going to look at that probability and see if it's unusual. Unusual would mean a low probability. Okay. So step number one is we're going to create what's called a test statistic. All right. We're going to create a test statistic. And that's that we're going to use a z formula. We're going to convert the p hat into a z using this formula. All right. And the test statistic indicates, whatever number we get, how many standard deviations that the sample statistic is from population proportion. All right. So when we calculate this, we get 5.08 as our z. And that's the number of standard deviations away from 0.5. Well, that's a lot. All right. I personally know what the answer to this question is going to be, but we're going to test it out. All right. Now, we're going to find what's called the p-value. Now, the p-value is the probability that this test statistic result, we would get this test statistic result, or something more extreme than that, when the null hypothesis is true. Okay? And that's how we're going to determine if this is a likely event with p is equal to 0.5 as our population proportion, or is it unlikely that we would get a sample statistic of 5.08? Okay. All right. So once again, p-value is the probability of obtaining a test statistic at least as inconsistent with h naught as was observed, assuming h naught is true. All right. I think I said it a little clearer than the slide here. All right. So in the standard normal curve, the z curve, that's what we're going to draw here. All right, 5.08 is way out to the right of for z. And remember, a standard normal curve has a mean of 0. So if we're getting a z-score of 5.08, it's way out here. Highly unlikely we would get something way out there. But anyway, what we're going to do is actually calculate the p-value. So 5.08, and what we're going to do now is I'm going to just exit the screen here. And I'm going to open up my TI-84 calculator. And what we're going to do is put that 5.08 into a calculator. Probability of p of z is greater than 5.08. To do that, we're going to use normal CDF. Always use normal CDF when we want to find a probability using a normal curve. 5 point is going to be the probability that z is greater than 5.08, so we'll put 5.08 as our lower bound. Upper bound, we'll use a large number like 1,000. The mean is 0, standard deviation of 1 for a standard normal curve. We hit enter. And look at the probability we get, 1.89. Now the e here represents the power 10. So this says 1.89 times 10 to the negative 7 power. That's called scientific notation. That means we move the decimal point to the left 7 positions, which means we're going to end up with 6 zeros, 0.6 zeros, and then if we round this up to a 2, you get a 2. So it would be 0.00000002. right? That's practically zero. It's really small number. So the probability of getting 5.08, z is as large as, at least as large as 5.08, is practically zero. So that's obviously highly unusual to get this 5.08 as for z. And what it really means, if we go back to the slides, what it really means is that it's to get the sample proportion of 5.8, the probability of getting that, or even more extreme, which is even bigger than that, given the mean of the normal distribution is 0.5, the probability of that happening is practically zero. So this is a clear case where we're going to end up rejecting the null hypothesis because it's practically zero that we're going to get a sample like this when we're assuming that the mean is 0.5. The population proportion is 0.5. All right. All right, so it says approximately zero for the probability. Since the p-value is so small, we reject H naught. There's convincing evidence to suggest the majority of adult Americans frequently check the nutritional labels on packaged foods. This is very convincing evidence that there's a majority. That is, we've rejected the null, and we've concluded that the highly likely result here is that p is greater than 0.5. Now, could we have made a type 1 error? In other words, when we reject the null, is it possible that the null is true? Well, it's always possible. But in this case, the probability of that happening is practically zero. Practically zero that we're making a type 1 error here. So that is why we're concluding that we're rejecting the null hypothesis, and we're concluding that very likely that the majority of Americans frequently check nutritional labels. So this is how we use our statistical data to come up with a conclusion. Okay. Now, in most cases, we don't get such convincing evidence when we do a hypothesis test. And so when we calculate our p-value, we really have to compare it to something. We have to compare it to something and make our decision, right? Because it's not totally clear. And what we compare it to is what's called the level of significance, or the probability of a type 1 error that we have determined up front before we do the research. So researchers, what they typically do, or they should do, is that before they actually do the study, they're going to come up with an acceptable alpha, an acceptable probability of a type 1 error. Remember, a type 1 error, the lower you go, the higher is the type 2 error. So we have to balance the type 1 and type 2 errors. We have to make sure that the type 2 error doesn't go up too much. So many researchers pick 0.05 or 5% as the reasonable significance level. We can change it if we want. We can go to 10% significance level, we can go to 1% significance level, or anything in between. But many researchers pick 5%. It seems to be a good balance between type 1 and type 2 errors. All right, so you pick that number up front, and then you make the following decision. If your p-value from the actual sample data is less than or equal to what you consider to be an acceptable type 1 error, the alpha that you pick, then your decision is to reject the null hypothesis. That it's okay to reject the null hypothesis. That's what I'm saying. Okay? If your p-value is less than or equal to your alpha, because alpha is considered acceptable, you're saying, all right, if I reject the null hypothesis, I'm going to accept up to a 5% type 1 error. Anything less than or equal to that type 1 error, it's okay with me. So if your p-value from the data is actually less than or equal to your alpha, you're going to say, okay, I'm good with that. I'm going to go ahead and reject the null hypothesis. However, if through your calculations, let's say you've up front you decided alpha is 0.05, and let's say your p-value is bigger than that. Let's say it's 0.23. It's bigger than 0.05. Well, that is an unacceptable type 1 error that you actually got, or possible type 1 error that you got from the sample data. 23% chance that you got that sample value or extreme. Okay, that's bigger than 0.05. That's bigger than what you consider to be an acceptable type 1 error. In that case, you're going to say, I'm kind of hesitant here. I don't think I have enough evidence from the sample data to reject the null hypothesis. I'm going to leave it alone. I'm going to say not enough evidence, because it's very possible here, because the p-value is so much bigger than alpha, or is bigger than alpha. It's possible this is just normal variation that I'm seeing these sample results. Normal variation when the null hypothesis is true. All right. So that's the decision rule. Let me repeat it again. When the p-value that we calculate is less than or equal to our stated type 1 error, then we reject the null hypothesis and support the alternative hypothesis. If the p-value that we calculate is greater than alpha, the acceptable type 1 error, then we do not reject the null hypothesis. We do not reject it. Okay? And that's our typical rule. All right, now, the calculation of the p-value depends on the form of the inequality in the alternative hypothesis. This is very important. Okay? It's our alternative hypothesis that will determine which p-value of the that we're going to calculate. In other words, which tail of the standard normal curve are we going to calculate our p-value from? For example, if our alternative hypothesis is p is greater than some number, that's the one that we just did, then we're going to use the right tail. Notice that the greater than symbol is pointing towards the right. See it? Pointing towards the right. So we're going to put our t, what we're going to do down here is we're going to put our test statistic down here, and then we're going to find all the area under the curve that is from the test statistic to the right, right? In other words, any z values that are as least as big as the z test statistic that we get, we want to find that area there, and that area is going to be the p-value. All right. All right. So this is called an upper tail test. Upper tail test. All right. Because our alternative hypothesis has a greater than symbol in it. What if we have a less than symbol in the alternative hypothesis? Notice it's pointing to the left. Yes, you're all right. You guessed it. It's a left tail test. In other words, we're going to find the probability of getting that test statistic or something lower than that, which is more extreme. And this area under here is going to be our p-value. It's the area in the lower tail. And then finally, the last possibility is that the alternative hypothesis has a not equal sign in it. That means it could be it could be that something smaller or a sample proportion that is smaller or sample proportion that is larger could be unacceptable when p is equal to some value. Population proportion is equal to some value. So we now have what's called a two-tail test. A two-tail test. In other words, our sample data is going to give us a z that's either positive or negative. If it's positive, what we're going to do is we're going to put it right here. We're going to calculate this area here. And that would be for the positive z. And then we would know that on the left tail, there's also a negative z of the same value. So this area here plus this area here, because both of these could happen, both of these probabilities need to be added together. And since they're equal to each other, we simply take the area that we got and multiply it by 2. In other words, the p-value, so if the z that we get is positive, we find this area here, we find this area or probability here, and then that's 1/2 the p-value. So we multiply by 2 because there's another area of the same type on the left side. Both of these areas need to be added together. If the z that we get is negative, we're going to do a left tail test, and that'll be 1/2 the p-value. So again, we multiply our result by 2. So I'll show you an example of a two-tailed test a little bit later. Right? All right, anyway. And then it says here, to decide whether or not to reject the null hypothesis, we can't compare the p-value to the significance level, alpha. That's what we choose up front. That's what I said a few minutes ago. And if the p-value is greater than alpha, we fail to reject the null. And if the p-value is less than or equal to alpha, we reject the null, for the reasoning that I mentioned earlier. All right. Here's our null. Here's our test statistic. Alternative hypothesis determines which of the tests that we do. If the alternative is greater than, we do a right tail test. If the alternative is less than, we do a left tail test. And if the alternative is not equal to, we do a two-tail test. And we have to make sure that when we calculate the area that we get, we multiply it by 2. Okay. Where does p hat come from? It's a sample proportion from a random sample. Remember that n times p and n times 1 minus p have to be greater than or equal to 10. Now, in this particular case, by the way, when we do hypothesis tests, since we have a hypothesized value for p, when we calculate n times p, we're going to use the hypothesized value, the number that's in our hypothesis test. We're going to put that in for p, not the p hat. Remember, this hypothesis test has to be determined if we can do it up front before we actually collect the data. So we don't even have the data yet when we do this. So our sample size times our hypothesized proportion have to be greater than or equal to 10, and so does n times 1 minus p have to be greater than 10. If this is true, then our sampling distribution of p hat is going to be approximately normal. Of course, we also have to make sure that if we are sampling without replacement, which we will do most of the time when we do surveys, the sample size cannot be more than 10% of the population size. And in most practical applications, it's always much smaller than 10% of the population size. All right, so what we're going to do next is we're going to do a couple problems, and then we'll illustrate the problems in the slides here, and then we're going to actually go through a few problems in the textbook before we end our discussion. All right. So it says a report states that nationwide, 61% of high school graduates go on to attend 2-year or 4-year college after graduation. Suppose you have a random sample of 1,500 high school graduates in 2009 from a particular state, and you estimate the proportion of high school graduates that attend college. And it comes out to be 0.58. Can we reasonably conclude that the proportion of the state's high school graduates who attended college is different from the national figure? So the national figure is what we're going to say is the population, the hypothesized population value. P is equal to 0.61 is going to be on null hypothesis. Now, it says here in the problem, can we conclude that the sample result is different from the national figure? Different. It doesn't say less than. It doesn't it doesn't say less than in this case here, or greater than. It says different. Different means not equal to. So immediately when we see the word different here, we're going to think of a two-tailed test. Now they're giving us alpha, this predetermined alpha before we actually did the study, of 1%. So we have a pretty small alpha here. And the whole idea is that from the sample data, if we get a p-value that is less than or equal to this 0.01, we're going to end up rejecting the null hypothesis and stating that the the state results are different, significantly different from the national results. So P here of 0.61% is our hypothesized value. It's the population value. We never ever put in a hypothesis test the sample data. Always the hypothesized population data. In this case, 0.61. All right. All right. And you can see that the null always is equal to, so P is equal to 0.61. It's definitely a proportion problem because we're dealing with counting people and proportions. And the alternative hypothesis is that P is not equal to 0.61, again, because we're using the word different here, which means not equal to. All right. Now, our sample proportion for the state that we're in, the sample proportion, 1,500 is our sample size. Our sample proportion P hat is 0.58. Okay. So, the assumptions, random sample. Yep, that's good. We want to double check that we can use the normal distribution for our sampling distribution. And the answer is yes, because if we multiply 1,500 times 0.61, we're going to get over 900. 1,500 times 0.39, we're going to get a little bit less than 600. They're both well over 10. So the sample size is large enough in this case so that we can use the normal distribution in the hypothesis test. Population size much larger than the sample size, you bet. Okay, here's our test statistic. Our numerator is going to be P hat minus P. What is P hat? The sample proportion. That's 0.58. So the first number is always the sample proportion minus the hypothesized proportion. We always pull it out of the hypothesis test. And the denominator is going to be the square root of P, our hypothesized proportion, 0.61, times 1 minus P hat, which is 0.39, divided by our sample size, which is 1,500. And when we do that, we calculate it to be negative 2.38. All right. Now, what we're going to now, because we have a two-tailed test, all right, and because our z is negative, remember a standard normal has a mean of 0. So this is over to the left. This is what we're going to do is we're going to conduct a left tail test, but the left tail area is going to be 1/2 of the p-value. Remember, for a two-tail test, we have to add the two tails together, two tail areas together. All right. Now, when we put this into our calculator, in other words, we use normal CDF, and we find the probability that z is less than negative 2.38, we get approximately a probability of 0.0087. You should try that out with your calculator. Make sure that's what you got. In other words, you're going to put in normal CDF, you're going to put in for your lower endpoint, you're going to put in negative 1,000, your upper endpoint will be negative 2.38, and then the mean is 0, standard deviation 1. And you should get a number close to 0.0087. But remember, that is the left tail area. With a two-tail test, we also have to include the right tail area, which happens to be equal to the same number. So we're just going to take that 0.0087 and multiply it by 2, and we get 0.0174. Very important for a two-tail test that when we find our area, we multiply it by 2. We do not do that for our left tail test or right tail test, only for a two-tail test. Now, since alpha is 0.01, 0.0174 is larger than alpha's 0.01. And so our decision is not to reject the null hypothesis because p-value is actually larger than our acceptable type 1 error. So we fail to reject the null hypothesis. All right? And we can just say that there's not enough evidence to suggest that the proportion of 2009 high school graduates in this state, okay, differs from the national level. Okay, just basically normal variation. Now, here's the thing. We picked a very low alpha here. All right? Notice that the decision would change if we picked a bigger alpha. In other words, if we had picked 0.05, as our acceptable type 1 error, then getting this p-value of 0.0174 would have been lower than 0.05, and we would have come up with the reverse decision. We would have failed to reject, we would have rejected the null hypothesis, and we would have concluded that there is sufficient evidence to conclude that the proportion of 2009 high school graduates differed from the national level. In other words, the proportion that attended college differed from the national level. So once we get the p-value, our decision really depends on what alpha was picked up front. In this case, alpha was very small, and we did not reject the null. But if we had, ahead of time picked a bigger alpha, like 0.05, we would have rejected the null. All right. So you might say that sounds kind of weird. Well, that's why it's important that we pick our alpha up front before we do the research. We don't want to fiddle around with the research results. In other words, we don't say, all right, I'm going to see what kind of research results I get first, and then I'm going to pick an alpha so that I reject the null hypothesis, which is the goal. No, in reality, if you're really doing honest research, you would pick the alpha up front and then see how things turned out. In this case, you picked a small alpha of 0.01, and your p-value was bigger than that, so you did not reject the null. Okay. Now, in this case, since we failed to reject the null, what potential error could you have made? Since our decision was not to reject the null, and if we had made an error in this case, that means we should have rejected the null. In other words, the null hypothesis is false. Well, if you remember, when we fail to reject the null, when the null hypothesis is actually false, that's called a type 2 error. And that's the type of error that could have happened in this case. Okay. All right. Let's do one more problem here, and then let's get to the problems in the book. We'll do just one more. I think we have time. In 2009, a countywide water conservation campaign was conducted in a particular county. In 2010, a random sample of 500 homes was selected, and water usage was recorded for each home. Suppose the sample results were that 220 households out of the 500 had reduced water consumption. The county supervisors want to know if their data supports the claim that fewer than half the households in the county reduced water consumption. So fewer, that tells me less than. All right. So this is going to be a left tail test. So it says fewer than half. Well, what's half? The proportion is 0.5, right? So 0.5 is going to be your the population proportion in your hypothesis test. Your null hypothesis will be obviously p is equal to 0.5. And since they use the word fewer here, fewer than half, the alternative hypothesis, p is less than 0.5. Now, what is the actual sample proportion? It's 220 people, households, divided by 500 homes or households. And I believe that's 0.44 is your p-hat. Okay, this is going to be a left tail test. Verify the assumptions, random sample. We multiply n times p, okay? N times 1 minus p. Is it reasonable that there are more than 5,000 households in the county? Yeah. That's why our sample size is small enough to do this. Calculate the test statistic and p-value. Here's our test statistic. We want to find the probability that z is less than this number. They say use the table. We would use normal CDF. We get 0.0037. Now, because this is a left tail test, there's a less than here. This area to the left, because we are doing a left tail test, the area to the left is 0.0037. In other words, the probability that z is less than this number is left tail. This is the total p-value. We don't multiply this by 2 because it's just a left tail test. If we used alpha as 0.01, p-value of 0.0037 is less than alpha is 0.01, and we're going to reject the null hypothesis. We're going to say there's convincing evidence that the proportion of households with reduced water usage is less than half of the population of households. What kind of error could we have made here? Since we rejected the null, it's possible that the null hypothesis is true. That's the type 1 error. That's what we did. But since the p-value, if this is the actual p-value we got, 0.0037, okay, and we up front we decided a 1% or 0.01 type 1 error is acceptable, then certainly a smaller p-value is also acceptable, and we're okay with rejecting the null hypothesis. That's all I do. All right, we're going to skip the confidence interval for this case here. I don't want to show that to you. This is a little confusing. Okay. All right, anyway, that's it. All right, so next time what we're going to do is we're going to do hypothesis tests for population mean. There will be a video on Monday for that. So that is it for the slides. And now what I want to do is go through some problems. And so let's spend the next 10 minutes or so going over some problems, and then we'll conclude the video. All right, so let's go to our textbook. All right, here we go. And we're going to look at first problem is, let me check my notes here. And it looks like almost there. Here we go. Number 25. Number 25. Here are p-values and alphas. And remember the rule, when the p-value is less than or equal to alpha, we're going to reject the null. When it's greater than alpha, we're going to do not reject the null. So let's just go through these quickly, just to give you an idea of how we make this decision. So they're giving you the p-value. So p-value is 0.084, alpha is 0.05. 0.084 is bigger than 0.05. Do not reject the null. So A, the decision is do not reject. B, p-value again is bigger than alpha. Do not reject. C, p-value in this case is less than alpha. Or excuse me, it's bigger than alpha, not less than. Again, do not reject. D, this is the one that is less than alpha. P-value 0.084 is less than alpha's 0.10. This is a case where we would reject. That's D. E, again, bigger than p-value bigger than alpha, do not reject. And F, again, the p-value bigger than alpha, we do not reject. So out of these 6 that are listed here, only D do we reject the null hypothesis. The other 5 we do not. Okay. All right. Now, what I'd like to do, so that's basically some practice using our decision rule of when to reject the null and when not to reject the null. Now, I'm going to show you a total of 6 steps to go through, and we go through hypothesis tests. I'm going to show you 3 hypothesis tests in the next few minutes. The first one's going to be number 29. Okay. This one right here. And we'll just answer part A, 29, part A. And again, I do have the solutions here, which I will post for you today. All right, I'll post that today for you, and I post the video. So let's go back to the problem, number 29. So we have a survey of 1,000 women, ages 22 to 35, who work full-time. 540 indicate that they would be willing to give up some personal time in order to make more money. The sample was selected in a way that was designed to produce a sample that was representative of women in this targeted age group. Okay. A, do the sample data provide convincing evidence that the majority of women aged 22 to 35 who work full-time would be willing to give up some personal time for more money? Test the hypothesis using the level of significance alpha to be 0.01. Okay, so this is determined up front that we're going to use alpha 0.01. Notice that they've talked about the majority of women. Majority means that P is greater than 0.5. All right, whenever you see the word majority, you know that's going to be your alternative hypothesis. P is greater than 0.5. All right, so what is our sample proportion? Well, it's 540 divided by 1,000. 540 said they'd be willing to do it out of 1,000 in our survey. So 0.54 is our sample proportion. Okay, so let's take a look at the steps that we go through to actually do a hypothesis test. Step number 1 is stating the hypotheses. The null, of course, is going to be P is equal to, we always put equal to there, 0.5. The alternative is going to be P is greater than 0.5. So whenever we see majority, we know immediately P is greater than 0.5. Step number 2, we're going to establish normality. Now, this is a random sample. We're going to conclude that the sample size of 1,000 is much smaller than 10% of the population size. So that's good. And then we have to see if n times P and n times 1 minus P are greater than or equal to 10, which they clearly are. Right? So that means that we can say that the sampling distribution is approximately normal. That's step number 2. We couldn't establish this, we'd be done. We wouldn't be able to do the hypothesis test. So step 2 is critical. Step 3 is we're going to calculate our test statistic. So the first thing that we need is p hat, right? Which is 0.54. And here's our formula for the z test statistic. P hat minus the mean of the sampling distribution of p hat divided by the standard error of the p hat. P hat minus p, since the sampling distribution mean is equal to the population proportion, you say p hat minus p, and then inside the square root, we're going to use our hypothesized proportion inside here with n. So p hat is 0.54, that's our sampling proportion, minus our hypothesized proportion of 0.5, divided by the square root of 0.5, times 1 minus 0.5, which is of course also 0.5, divided by a sample size of 1,000. And our z statistic is 2.5298. Now, since this is a greater than problem, we're going to use a right tail test. That's going to be step number 4, is we're going to determine, do our actual test. That is, calculate the p-value. So we have our test statistic now. That's step number 3. Step number 4 is we're going to plot that test statistic on a standard normal curve. It's a right tail test, so it's going to be the right tail. Since it's a one tail test, this whole area this whole probability or area is going to be our p-value. We're going to use normal CDF, and we're going to say, since it's greater than, it's going to be 2.5298 lower boundary, 1,000 upper boundary, 0,1 mean and standard deviation for standard normal. We get 0.0057 as our p-value. Step 5 is we compare the p-value to our alpha. It's much smaller than the alpha, so we're going to reject the null hypothesis. And step 6 typically is an interpretation. In the interpretation, we always state the level of significance. So we would say something like, at the 1% level of significance, there is sufficient evidence to support the claim that a majority of women ages 22 to 35 who work full time would be willing to give up some personal time for more money. That could get cut off a little bit at the bottom there, but as you can see the words. All right, the next one would be 10.32. Let's go back to the book. And it's 10.32 is on the next page. In a survey of 1,005 adult Americans, 46% indicated they were somewhat interested or very interested in having web access in their cars. Suppose that the marketing manager of a car manufacturer claims that this 46% is based only on a sample, and that 46% is close to 1/2. Okay. So there's no reason to believe that the proportion of all adult Americans who want car web access is less than 0.5. Is the marketing manager correct in this claim? Well, the test, in this case, the marketing manager is hoping that the null hypothesis is true, that it's 0.5 is the proportion, but we're going to use as the alternative hypothesis. We're going to check to see if the marketing manager is incorrect. So we're sort of the researcher in this case. And this is going to be, we're going to see if the value is less than 0.5. Notice the data anyway in the study shows that it's less than 0.5. It's 0.46. This 46%, by the way, is our sample proportion, and 0.5 is going to be our hypothesized proportion. Remember, we never use sample data in our hypothesis tests. All right. Let's, oops, wrong one. 32. In this case, our alternative hypothesis is what we're going to be using as a researcher, is that P is less than, I don't want this, so let's get out of here. Sorry about that. This suddenly appeared out of nowhere. But P is less than 0.5. All right, is our alternative hypothesis. So if you see that as a researcher, we want to determine if the proportion is less than this, and then if it is less than it, then we've disproved what the marketing manager is saying. Can we do the test? Yep, we can do it because 1,005 times 0.5 is well above 10, right? In both cases here. So we can use the normal. He had his 0.46. Again, we're going to use this formula and plug in 0.46 is our sample proportion minus the hypothesized proportion, 0.50. Here's our denominator, and here is our calculated test statistic. In this case, it's a negative number, right? 0.46 minus 0.5 in the numerator here, which is negative. So it's consistent with, of course, this left tail test. We're going to plot negative 2.5361 on the left here. We're going to use normal CDF, do a left tail test, and we come up with, again, a small probability of 0.0056. Step 5, we're going to compare that to our alpha, a point, and the problem didn't give us an alpha, but let's assume it's 0.05. This is well below alpha 0.05, so we're going to reject the null. And here's our conclusion. Sufficient evidence at the 5% level of significance. There's sufficient evidence to reject the marketing manager's claim that the proportion of all adults who want car access is not less than 0.5. That's what the guy was saying. He's saying it's normal variation around 0.5, and what we found is that it's not normal variation about 0.5, which the probability of getting 46% in a sample is significant. It has a very small probability if we assume that the population portion is 0.5, so therefore we're going to reject that 0.5. We're going to say it's something small for our population. And finally, the last thing we're going to do is, and again, I only have a couple minutes because I do have a Q&A right after this, so I just want to make sure we have enough time, is 10.34. And 10.34 is an example of a two-tailed test. A report says that 37% of teens in the US access the internet from their mobile phones. Obviously, this is quite a few years ago. Now it's almost everybody, but let's assume that's true. All right. All right, so that is our population proportion. All right, it's a report, but it's not based on any sample data. Suppose you plan to select a random sample of 500 students, and you want to check this out, right? And in this case here, you plan to use the data to decide if there's evidence that the proportion, all right, differs from this national figure of 0.37. Here's the word differs here. That should tell you it's a two-tailed test. Differs means it could be less than, could be greater than. What hypothesis would you test? Well, this is the population proportion The null is going to be p is equal to 0.37. Our alternative is going to be p is not equal to 0.37. So let's go ahead and put that into our solutions here. This is going to be a two-tail test. Again, n times p, n times 1 minus p, well above 10. So we can use a normal distribution for the sampling distribution. Step 3 is we're going to calculate our sample proportion. And they didn't give you sample data here because they didn't ask any of this. I'm actually developing an entire problem here that wasn't asked in the textbook. So suppose that 177 of the 500 students surveyed state that they have access to the internet. Suppose, so if we divide these two numbers, we get our sample proportion. Suppose we plug that into our test statistic, and we get negative 0.741 as our test statistic. Step 4, we have a two-tailed test here because our alternative is p is not equal to 0.37. So we're using negative 0.741. This end here, but note that there is a positive 0.741 also because it's a two-tailed test. But anyway, we're going to find the probability that z is less than negative 0.741. Notice in a two-tailed test, that's going to be 1/2 the p-value because we have the other end also, which is the same area. When we calculate this left area here, it's 0.2293. We multiply it by 2, and this is the actual p-value because this area on the left is 0.2293. This area to the right is also 0.2293, and that means the p-value is 0.4586. Let's assume that alpha is 0.10. This p-value is much larger than alpha, and our conclusion, do not reject the null hypothesis. And this is how we would write it up. At the 10% level, there's not enough evidence to conclude that the proportion of students at the local high school differs from the national average. Okay. Anyway, that's it. That's examples of how to do hypothesis tests through the 6 steps. Once again, you'll have access to all of this to look through the steps again. Again, we'll have more practice with this next time. Next time, we're going to do hypothesis tests for population means, okay? And that'll be our next Monday. All right, so anyway, I'll stop sharing, and I will see you, since I now have to run over to another part of my computer to do a Q&A. I will conclude, and I will see you next time. Take care.